Good morning, students. Contribution of deep dark elements. We will see the specific properties of transition elements. In last class, we saw the variable oxidation state. Now we are going to explain some important points of variable oxidation states. These are all important specific properties of transition element. Second one, magnetic properties. Magnetic properties, color properties, complex formation properties, alloy formation properties, catalytic properties. These are the important specific properties of transition elements. Last class we discussed about the variable oxidation states. That means, what is the meaning of variable oxidation state? An element exhibits more than one oxidation state, we called variable oxidation state. Why those exhibit variable oxidation state? Due to the availability of d orbitals, due to the availability of unpaired electrons and vacant d orbitals, and what we call high nuclear charge. Due to the high nuclear charge, these elements are variable oxidation states. In continuation, just I want to do the highest oxidation state of the transition elements. Highest oxidation state of transition element is +8. It is present in osmium tetroxide, ruthenium tetroxide. In ruthenium tetroxide and in osmium tetroxide, it exhibits the +8 oxidation state. Here oxygen -2 into 4 -8. Here osmium exhibits +8 oxidation state. Here ruthenium exhibits +8 oxidation state. Anywhere in highest oxidation state of any atom always available in the form of oxide or in the form of fluoride. Why? Because that much oxygen atoms, that much fluorine atoms provide only for which has more nuclear charge. That only provide space to those atoms. And one more, these are also form the attraction forces between nucleus of the central metal ion. Why? Because these are more electronegative. Here oxygen second highest more electronegative, fluorine first highest more electronegative. This is very small atomic size containing element. After second one is this one. Due to small size, one is small size, second one is more electronegative, negative nature of fluoride and oxygen. All transition element, highest oxidation, which element exhibit highest oxidation state? Those available in fluoride form and here oxide form. Due to only two reasons. One is small atomic size of fluorine, second one is small atomic size of fluorine and oxygen, second one is more electronegativity of fluorine and oxygen. That's why these exhibit highest oxidation state in oxide form or fluoride form. This was the just discussion of the variable oxidation state. Then in continuation, we will discuss about the magnetic properties. What is the meaning of magnetic property? What is the magnetic moment? What is the magnetic nature? We will see in continuation. Magnetic properties. Second one is magnetic properties. Okay, here the attractive nature of any an element we simply considered as a magnetic property. Attractive nature, opposite to the attraction is repulsion. Repel nature or attraction nature of any element, could be considered as a magnetic nature. The element which exhibit the magnetic property that we call as magnetic properties. Okay, based on the magnetic behavior of an atoms, these all our atoms or transition elements classified into three types. Transition elements classified into three types, or elements classified into three types. One is diamagnetic substances. Second one is paramagnetic substances. Okay, third one is ferromagnetic substances. Ferromagnetic materials, ferromagnetic elements, ferromagnetics, paramagnetics, diamagnetics. What is the diamagnetism? What is the paramagnetism? What is the ferromagnetism or ferromagnetics? Okay, here suppose I am taking one magnet. This is a magnet. This is an element. If an element repelled from the magnet, such substances we call as diamagnetic substances. Repel means, suppose this is an element, this is a magnet. Okay, like this. This is repel like this. Repulsion subsoil. This type of materials we call as here diamagnetic substances. The molecule which have paired electrons. The molecules which have paired electrons, all those exhibit the diamagnetism. Suppose zinc, cadmium, mercury. All these exhibit in normal form, these exhibit the diamagnetism. Why? Because all these contain completely filled orbitals. Okay, here zinc is the 3d10, cadmium is the 4d10, mercury is the 5d10. Completely filled orbital. Due to the presence of completely filled orbitals or paired electrons, these molecules exhibit the diamagnetic in nature. Not only this, some of the molecules are there which have the paired electrons in outermost orbit. So all the transition elements exhibit diamagnetism. Okay, paramagnetism. Here I am taking magnet. Okay, here I am taking element or transition element. Weakly attract. The material, the element which is weakly attracted by the magnet, are called paramagnetic materials or paramagnetic substances. Okay, example for paramagnetic substances which have the unpaired electrons. The element which have the unpaired electrons, those exhibit paramagnetic nature. Suppose for example, here I am taking Cu plus 1, Cu plus 2, which is paramagnetic, which is diamagnetic. Cu plus 1 means 3d10, Cu plus 2 means 3d9. It has completely filled orbital, so it is diamagnetic substances. It has unpaired electrons, so it is paramagnetic substances. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have lone pair of electrons. So it is a Cu plus 2 is paramagnetic substance. Cu plus 1 is diamagnetic substance. Here lone electron is there, unpaired electron is there. Due to the presence of this unpaired electron, this molecule weakly attracted with the magnet. This element weakly attracted with the element. Here diamagnetic substance, water is also diamagnetic substance. Water is also one of the best examples of diamagnetic substance. So many iron is attracted more and more. That's why it is considered as a ferromagnetic substance. Okay, these are the which have uncompletely paired electrons that exhibit diamagnetism. The element which have unpaired electron that exhibit paramagnetism. Next is ferromagnetism. Okay, the elements which strongly attracted with the magnet, are called ferromagnetics. That phenomenon is called ferromagnetism. The element which exhibited by the ferromagnetic nature we call as ferromagnetism, paramagnetism, diamagnetism. Okay, here see example for this: cobalt, nickel, iron. These are iron, cobalt, nickel. These are the important ferromagnetic. These are strongly attracted. The nature of the element is strongly attracted by the magnet. That's why those are simply considered as a ferromagnetics. And the magnetic nature of any element explained by using magnetic moment. The magnetic moment indicated with mu. The units for magnetic moment is Bohr magnetons. The magnetic moment of any element calculated by using one principle. We'll see in continuation that principle. The magnetic moment. What is the magnetic moment? The magnetism of an element. Okay, the magnetism of an element explained by using magnetic moment. Magnetic moment indicated with W. Magnetic moment indicated with mu. Mu is calculated by using this principle, under root n into n plus 2. N into n plus 2. Okay, here Bohr magnetons are divided. Okay, here magnetic moment of an element depends on number of unpaired electrons. Magnetic moment of an element depends on number of unpaired electrons. Here I am taking number of unpaired electrons, and here I am taking mu value. In examination point of view, NEET point of view or JEE point of view, they may ask what is the magnetic moment of particular element or ion. Like that. Okay, we'll see the magnetic moment values. 0 electrons are present. That means no unpaired electron is magnetic moment is 0 Bohr magnetons. Okay, if one lone electron is there, 1.73 Bohr magnetons. Okay, if 2 lone electrons are present, 2.84 Bohr magnetons. Okay, if 3 electrons are present, the magnetic moment is 3.87 Bohr magnetons. Okay, 4 lone electrons are present, the magnetic moment is 4.90 Bohr magnetons. Okay, here 5 electrons are present in that. Okay, 5 unpaired electrons present in molecule or element, the magnetic moment is 5.92 Bohr magnetons. These are the different values. Okay, these are the different values, okay, of different elements based on the number of unpaired electrons. Suppose for example, here I am taking Cu plus 2. Cu plus 2 ion, we call it cupric ion. Cu plus 2 ion, we call as cupric ion. What is the outermost electronic configuration of cupric ion? First write copper. Copper electronic configuration, atomic number 29. Outermost electronic configuration I am writing. Okay, our complete electronic configuration argon 3d10 4s1. Okay, I write this right. Systematic format 4s1 3d10. Cu plus 2 means remove 2 electron, 1 electron from here, 1 electron from here. What will get? Argon. Okay, 4s remove 3d9. Write 3d9 electronic configuration. 1, 2, 3, 4, 5 or 6, 7, 8, 9. Here we have only one unpaired electron. One unpaired electron. And what is the magnetic moment of Cu plus 2? Then I ask one more question. Okay. What is the magnetic moment of Cu plus 2 ion? What is the magnetic moment? If one electron is present, the magnetic moment is 1.73 Bohr magnetons. If we use this formula also, we get same. But instead of formula, you remember this one. Okay, Cu plus 1 plus 2 is the magnetic moment of Cu plus 2 is 1.73. You take Fe plus 2 or Fe plus 3. Fe plus 2, 3d6, 4s2, Fe iron, remove 2, 3d6. Okay, iron electronic configuration is 3d6, 4s2. Okay, Fe plus 2, 3d6. 3d6 means how many lone electrons are present here? See, 1, 2, 3, 4, 5, 6. 4 lone electrons are present. 4 lone electrons means 4.90 Bohr magnetons. Fe plus 3 is there. 3d5. Here 1, 1, here 2, 3. Remove. Fe plus 3. 3d5 means 5 electrons, 5 lone electrons are present here. 1, 2, 3, 4, 5. 5 means what we call the magnetic momentum of Fe plus 3 is 5.92 Bohr magnetons. Should write the units. Based on the number of unpaired electrons. Based on the number of unpaired electrons, we will calculate here. Okay, magnetic moment. Suppose for example, zinc plus 2 is there. Zinc 3d10 4s2. Remove 4s2. We have zinc plus 2 has completely filled orbitals. 0 lone electrons, so 0 Bohr magnetons. One more question they will ask. They will give the ion. And they will ask magnetic moment of that particular element, transition element. Okay, this is about the magnetic moment. Then in continuation, we will see the one more important property, color properties. Color properties. Okay, some of the Dirac elements shows color properties. Why they shows color properties? First, I will give the reason. There are 3 marks information. Why transition element shows color properties? First reason is availability of d orbitals, and here presence of unpaired electrons, which are only unpaired electron, those only shows color properties. Those transition elements shows color properties. And here d electron transition. Here we observe d electron transition, and here high nuclear charge. High nuclear charge. Due to these reasons, all transition elements exhibit color properties. We'll see. Okay, here we'll see which element exhibit which color. And okay, see, first point, first reason, second reason, third reason, and fourth reason. First, I am giving ion and color, and in continuation we discuss number of lone electrons. After that, we will see what is the d electron transition. Just I will write the colors of the ions. One is scandium +3, colorless. We'll see how many lone electrons are there. Titanium +4, colorless. Next, vanadium +4, blue color. Vanadium +3, green color. Vanadium +2, violet color. Chromium +3, violet color. Chromium +3, violet color. Manganese +2, violet color. Manganese +7, pink color. Manganese +7, pink color. Okay, next, in continuation, Fe +3, yellow color. We'll see number of lone electrons. Okay, Fe +2, green color. Next, cobalt +3, blue pink. Next, nickel +2, green color. Next, Cu +2, blue color. Next, zinc +2, colorless. Zinc +2, colorless. Okay, these are the different colors of different ions. First, all are having colorless means should contain the paired electrons or unavailability of d orbitals. For example, scandium atomic number 21, 3d1, 4s2. Remove 3d1, 4s2 means 0 unpaired electrons. 0, 3d1, 4s2 na. 3d1, 4s2 means remove 3 electrons. So 0 unpaired electron. That's why it is colorless. Titanium +4, titanium 22, 3d2, 4s2. Atomic number titanium 22, 3d2, 4s2. That means it loses 4 electrons. That means here also 0 electrons in outermost. That means completely filled. 0 unpaired electron, 0 lone electrons are present in outermost orbit. So colorless. Vanadium +4. What is the vanadium atomic number? Okay, here 3d3, 4s2. Okay, it removes 4. 4 means here 2, 1 is there, 3d1. 3d1 means one lone electron is there, so blue in color. Here vanadium plus 3, 2 lone electrons are present, green in color. Vanadium plus 2, 3 lone electrons are present, violet color. Violet color. Chromium plus 3, chromium atomic number. Okay, chromium 3d5, 4s1. Cr plus 3, here 1, here, okay, here 2. Total remove 3. 3 means 3d3. Total 6, remove 3, 3d3. 3 means 3 lone electrons. 3 lone electrons means violet color. 3 lone electrons means violet color. See, manganese plus 2. Mn 3d5, 4s2. 3d5, 4s2. Manganese. Chromium 24, 3d5. Remove 2. 5 electrons are present. 5 lone electrons are present. Exhibit violet color. Mn plus 7. Mn plus 7. It also exhibit Kmn4. Sorry, it is colorless. Next, Fe plus 3. How many lone electrons are present in Fe plus 3? Fe iron atomic number 26. 3d 6, 4s2. Remove here 2, 1 here 1. That means 5 lone electrons. Yellow color. Okay, here Fe plus 3. 3d 6. Okay, only 4 lone electrons. Green color. CO plus 3. CO cobalt 3d7, 4s2. Plus 3 now, here 2, 1. 6 means 4 lone electrons. Blue pink color. Here nickel plus 2. Okay, nickel plus 2. Nickel means 3d8, 4s2. 8 means 2 lone electrons. Green color. Cu plus 2, 3d10, 4s2. 3d10, 4s1. Remove 1 electron. 2 na? 2 means 9. 9 means 1. Blue color. Zinc plus 2, 3d10, 4s2. Zinc electronic configuration. Remove 4s2. Only 3d. Completely filled. Colorless. Here completely filled colorless. Here completely filled colorless. Here completely filled colorless. Here completely filled colorless. Here we have the lone pair electron. Where the lone pair electrons are there? Those exhibit the color properties. Those exhibit the color properties. And one more thing, all the ions, all the elements, all the transition element shows color properties in hydrated state only. Hydrated state only. Suppose for example, cupric sulfate, anhydrous cupric sulfate, colorless. Hydrous cupric sulfate is a blue in color. Why? Because when it is added with the water, it releases Cu plus 2 ions. Then only it exhibits color. If it not releases Cu plus 2 ions, it never exhibits the color property. So, all the elements, all the transition element compounds shows color properties, their hydrated state only, not in anhydrous state. Okay, here one is agarity of d orbitals, finish. Presence of unpaired electrons, finish. High nuclear charge means, okay, number of protons more, number of electrons is less compared to that one, compared to the electrons and protons. So high nuclear charge is present in this ion. One more we see important point, due to the dd electron transition. Due to dd electron transition. What is the meaning of dd? D orbital to d orbital. D orbital to d orbital. By the dd electron transition, okay, these elements exhibit the color properties. We'll see dd electron transition here. d electron transition. Due to this only element exhibit color properties. Okay, for example, I am taking Cu+2 ion, blue in color. Okay, in hydrated state only, not in anhydrous. Anhydrous means never releases Cu+2 ion. In anhydrous state, they never releases the ions. So colorless. In hydrated state, they will release ions. So, okay, colored. Okay, here I am getting outermost electronic configuration of copper+2. Copper+2 means argon. Copper means argon 3d10 4s1. Copper+2 means 3d9. This is the outermost electronic configuration of copper. This. Okay, here 1, 2, 3, 4, 5, 6, 7, 8, 9. Here we have the lone electron. What it does? What this lone electron can do? How we observe the dd electron transition? All these orbitals, these d orbitals having same energy. All these d orbitals having same energy. All these d orbitals having same energy. We called degenerate orbitals. Degenerate orbitals. Here 2, here 2, here 2, here 2, here 1. When these degenerate orbitals absorb the energy, one energy absorbed, that means it exposed into sunlight. It absorbs the one colored energy in Vijaya, from the Vijaya. It absorbs one color energy from the Vijaya and splitting into two types of orbitals. Splitting into two types of orbitals. One is higher energy orbitals. These are the higher energy orbitals. These are the lower energy orbitals. Here higher energy orbitals are called Eg orbitals, interdigit orbitals. Lower energy orbitals are called T2G orbitals, triply generated orbitals. Eg, interdigit, okay, easy generated orbitals. Okay, here triply generated orbitals. Here 1, 2, 3, 4, 5, 6, 7, 8, 9. Electron, one of the electron, when it absorbs the energy, one of the electron get excited into higher energy level. Okay, in higher energy level, that particular electron unstable. Okay, for example, this absorbs the yellow color energy, and it gets excited into higher energy level, that we call Ag. Again, this electron come back by the releasing of energy. That energy we absorb by our eyes. This is absorbed color. That energy only absorbed. This is the absorbed color. What is the absorbed color of copper? Blue color. This is emission energy. What we are observing color, that color we call as emission energy. Okay, here it absorbs the energy from the Vidya. This color we called complementary color. This color we called as complementary color. Okay, an element which absorbs the color from the Vidya we called complementary color. The element which emit and which shows a particular color we called as absorbed color. See what you observed here? Electron transition involves in transition from lower energy level to higher energy level. This electron transition we call as d orbital electron transition or d electron transition. Due to this d electron transition, d black element shows color properties. Okay, this is about the color properties of d black elements. In continuation, we'll see some more important properties. Okay, some more specific properties of transitional elements. Thank you.